So let us start a new chapter, and it's called circles. But it so happens that most of it deals with tangents. Okay, so either way, let us start with the first two theorems which are required to solve the problems here. Even before we go to the theorems, there is one basic assumption, a basic kind of a concept which we need to understand. And the concept is this: if there is a straight line and if there is a point, then the shortest distance between the straight line and the point has to be a perpendicular distance. That is, if you drop a perpendicular from the point, let's say P, to the straight line L, then this is the shortest possible distance. Now logically it's not very difficult to get. Let's say this is the perpendicular. Okay. Now if you draw any other line, take any point other than this point, let's call it T, any other point, then all these points are hypotenuses of different right angles that they form. So for example, I take a point here, right here. Now if I join this is a hypotenuse of this right angle, so therefore this has to be longer than PT. Even if I take a point just very very close to T and join, even then I'll form a very slim right angle triangle, and this hypotenuse is going to be longer than PT. Remember, in a right angle triangle, hypotenuse is the longest side. So from this, it's kind of obvious that the shortest distance has to be PT. Let me review. The shortest distance between a point and a line is always the perpendicular dropped from the point to the line. Okay. Now this can be connected to a very simple phenomena of dropping something under the influence of gravity. Let us look at that. So here we have a small object, and you will see that when I release it, it takes the most optimum path, the shortest path between where it is to the plane below. So now let us try to understand the theorem. So what does the theorem say? The theorem says that the tangent at any point on a circle is perpendicular to the radius through that point. Now how do we prove that? Let's have a look. So the point is P, and remember, by definition the tangent touches the circle at only one point, and that point is called P. Of course, when we are drawing it, that's more difficult to show. Okay, but you have to remember that conceptually this line is touching the circle at only one point, P. Now we have to prove that OP is perpendicular to AB. So how do we prove it? First, let's just take a few points outside P or away from P. P, P1, P2. We can take it as close as P as we like, but away from it. Now take all these points, right? Now if you join a line, say OP1, now P1 will be outside the circle, therefore OP1 will be greater than the radius, right? So we can say OP1 is greater than OP because OP1 is greater than the radius. Similarly, OP2 will be greater than OP, correct? Because again, it's outside the radius. And this logic can be extended for all points on AB except P, right? This will be true for all points except P. Therefore, OP is the shortest distance between O and AB. So I hope the logic is clear. If you don't take P, if you take any other point on the left or the right, you'll always find that that point is outside the circle, and therefore OP1 or OP2 or OPN, whatever it may be, is greater than the radius. That obviously means that the radius OP is the shortest distance between the line AB and the point O, the center O. Therefore, we can say that OP is perpendicular to AB. What's the logic? Just what we had discussed in the beginning. Since the shortest distance between a point and a line is a perpendicular distance. So this is the proof for the theorem which says that a tangent is always perpendicular to the radius through the point of tangency.